Okay, so 2.8, Unit 2, this is the higher derivatives. So you can't have an f prime of prime, which means f double prime, which means the second derivative. Okay, 2 ticks, 2 derivatives. Okay, come on, that's not that complicated. Okay, so all this is the derivative of the derivative. Okay, because dy over dx, remember, and this right here, I always say his name wrong, but Leibniz, okay, notation is going to be important for 2.7. Okay, we're going to use that quite a bit. Understand dy dx stands for f prime. And if you take the derivative of that, okay, that's a double derivative. Remember, d over dx is the derivative with respect to x. Okay, yeah. Okay, you can, and that's why that's here. That's the other way of writing it. Okay, that's the other way of writing it, because the reason that you can do it this way is because if you take the derivative with respect of x, usually y is by itself. So you're taking the derivative of what's over here, the x's, so you don't really have to do the dy part because there's no y there, because derivative of y would just be y prime. That wouldn't really make sense. So this is more what you're talking about, d squared y over dx squared. That's that squared. Okay? All right, so then here's all the different ways you can write it. Y double prime, f double prime, d squared y over dx squared. Okay, derivative squared f of x. And I wouldn't ever use that one, so don't worry about that one. Double prime. Yeah, f double prime, the 2 ticks. That's the same thing as the second derivative, yeah. Okay? All right? You're going to be moaning until we do it, and you're like, well, that's dumb. Okay, so now it wants d squared y dx squared. Okay? We want to find y double prime. So what's y prime? 6x5. Now, what's y double prime? We're taking the second derivative. You're done. Take the derivative twice. I told you we weren't really killing things here. Okay? Take the derivative twice. Okay? So remember, I just use power rule. If you're, not quite seeing it, drop the 6, subtract 1, that's 5. Drop the 5, there's already a 6 there, times them. That's now a 4. If you put the same number in... Oh, do these mean the same thing? No, they don't. We'll talk about that in a second. That's what Morgan's asking. Let me get to that in a second. Right now we're just practicing the technique. Let's get to the definition of what we're doing. It'll be right down here. No, this right here, that's our equation. This is the equation of the tangent line still. Just like with the slope of the tangent lines. That's still the same. We'll talk about what the second derivative does. Okay? Tangent slope. Right. Right. Because remember, limits were the definition of derivatives. So now limits are kind of somewhat pointless in a way to us because we have derivatives. Okay, so find the second derivative of this guy. So now we still use the sum difference rule, which means we just do it piece by piece. Okay, so our first prime here would be 10x, and then we know what the square root of that is, don't we? Or not square root. We know what the derivative of root x is by now, don't we? 1 over 2 root x. Okay, again, for those of you who haven't been here, that's x to the 1/2. I drop the 1/2. I get x to the negative 1/2. That puts it on bottom, which is just a positive. Because whenever you take derivative, you minus 1 from the exponent. But it'd be negative 2/3 because it's not quite half. Because 1/3 minus 1 is 2/3, so it would be a little different. 1/2's kind of a nice pattern because it's 1 half to negative 1 half. Okay, and the second derivative, what's the derivative of this now? Just 10. How would you want to write it?
I just thought that wasn't the most simplified form.
No, it is, because you could multiply root x at top and bottom, but then you just kind of actually create more work for you. A good point that Rachel said is whenever you have a radical on bottom, it's not necessarily a bad thing in calculus. So don't think you have to rationalize every time. Especially wait till you're done. Okay, one of my biggest problems with calculus is that I'd always try to oversimplify, and then I'd make my life harder. Like, for example, if she went ahead, like Rachel, if you went root x times root x, well, we have to take the derivative again. So now you just create a quotient rule. So we'd have to do a quotient rule on your new one. Okay, and we don't want to do that.
How do you know when to stop simplifying then?
Yeah, like I would just say there isn't really a right or wrong in terms of simplifying. If you get the equation, it's good. The only time that you need to simplify more is if there's stuff that you could cancel, or like if we're looking at a number that doesn't work at that point. Like, we plug 2 in, you might have to cancel stuff. So I think in terms of when you simplify the most you can, just do the most you possibly can, and then if that's as far as you can go, just leave it. I don't think there's a right or wrong for that. Okay. So, but anyways, this one, I'm just going to write this though as 2x to negative 1 half, just for the sake of doing the derivative again. Yep. The 2. The what? The 2. This. Right. And where's the negative go? Bottom. What's a 1 half? Square root. Right now? Yeah, right now I just flipped it. I'm not done yet, so actually I wrote that in the wrong spot. This guy right here isn't the derivative yet. Sorry. Maybe that's what you're talking about. My problem right now, you don't know. We did. Oh, I see what you're saying. Yes. So we can just go ahead and go from here. Yes. This 2? It's 1 half from dropping the 1 half. But what 2 are you talking about? Are you talking about this? This guy?
When you wrote it in the second derivative equation.
Yeah. Oh, right here? Oh, okay. Sorry, yeah, it should have been over 2. Sorry. Should have been over 2, Emily. You're right. Okay, so it should be like this. This is what it should be anyways, because this is our first derivative, and we're going to do it again. So if you drop a negative 1 half, what's 1 half times a negative 1 half? Or, excuse me, negative 1/4. Okay, now I subtract 1 to that, so what's that now? Yeah, negative 3 halves. Okay, so that's what the second derivative of that is. So simply, all you do is plus a negative 1/4 x to the 3 halves. You can leave it like that, and that's fine. So that's your second derivative.
And it isn't the negative 3 halves because you dropped it down.
It's to the positive 3 halves. That's why, yeah.
Because it was the negative.
It was negative. I moved it down to make it positive, yes. Okay. Okay, so one more, and then we'll talk about what the second derivative actually does for us, since that seems to be the common question. Okay, all right, so now this one, we have to do it twice, and it's connected to the what? What rule are we going to be using? Chain rule. Okay, so we got to do chain rule. So first, we got to do f prime 1, and they're telling me what to evaluate at. So when we get f double prime, we're going to plug a 1 in. Okay, so the first thing you're going to do here, drop the 10. 2 minus x squared to the 9th. Okay, and I have to derive the inside, so that's the chain rule, which is going to be negative 2x. That's f prime. Chain rule is the one where you take the derivative of the outside times the derivative of the inside. So the outside would be, treat this like that's a x. I drop the 10, make that a 9. Just put that's what this is here. And then I have to derive what's on the inside of it. Derivative of the inside is just negative 2x. So derivative, we'll call it derivative of the outside times the derivative of the inside is chain rule. And that was Friday, Monday. Now we have to do product rule, because we have a product with two x's. Chain rule on Friday was first day. Okay, so f of double prime, we have to do the product rule. So remember, first derivative second, second derivative first. Emily? We have to use chain rule as well, because these are two pieces. Yep, that's what happens all the time, guys. Yep. Okay, so you're getting yourself confused. Watch what happens, okay? Because right now, okay, you guys are asking good questions. We have these two pieces, right? You know the pattern goes first derivative second. So the first, I just write this. And yeah, we're doing product rule, yep. We have to do chain rule. Yes. So see what I'm saying? It kind of just happens. Okay, so what Emily's talking about, she says, like, how do you know what to do first? Morgan identified this is product rule. So we're doing product rule. So we're doing first times derivative second. So I write the first piece. This is the first piece. That's the second piece. I just write this. What's the derivative of the second piece? Negative 2. That part's done. Plus second times the derivative of the first. Now I have to do the chain rule again. Drop the 9. That makes 90. And then it gives me, I'm running out of room here, 2 minus x squared to the 8th. Here, let me write this below. So it's 90, 2 minus x squared to the 8th, and then what's the derivative of the inside? And again, negative 2x. Okay? Go ahead. So we dropped the 9. That's 90. The 9 now becomes an 8. I have the inside. I have to do the derivative of the inside again. We've already done. Yeah, right here. It's this. All this stuff is multiplied to this guy, and then this is added right here. Okay? Why do we do both, like sections? And this? We have to do the chain rule again. Okay, we'll do the chain rule one more time, so we still get that negative 2x again. I see what you're saying, but it happens again. Okay, so this point, guys, at this point, since we have it done, we don't have to worry about simplifying because it gives us a number. All we need to do is just plug in our number now, because this is a derivative. Okay, so I'm going to have 10 times, 1's easy, so that's nice, 1 to the 9th, which is just 1, times a negative 2, plus negative 2 times 1 is a negative 2. I have a 90. I have, again, a 1 to the 8th, and I have a negative 2 again. So that's going to be negative 20 right here. And then this guy is going to be negative 180 plus 360. So your answer for this is 340, and that's correct. That's what I got in my notes. So we just evaluated at f of double prime of 1. Okay, the second derivative of 1. You can, but since we already have a number, it doesn't really help you, because we don't need to simplify it because we just can plug it in. But yes, that pattern you were talking about yesterday in your homework, you could do that. Okay, anything else before we get to what the second derivative actually is? Okay, all right. So since the first derivative, the function can be interpreted as either the slope of a tangent line, so that's what I told you guys, slope of the tangent line, or as a rate of change. That's what we did too with the velocities and stuff. Okay, it could be either or. The second derivative can be interpreted as the rate of change of the slope. So as our tangent slope, because we get tangent slopes, they're different for every line, right? Our tangent slope has an equation of lines. Well, that thing also has a rate of change. Okay, so it has a rate of change of how it's changing. So that's why I said it might be confusing, but it's the rate of change of the rate of change. Okay, how is it changing? This idea we'll pursue further in Chapter 5. Okay, it gives valuable information on the shape of a graph, and other application occurs in Chapter 3. So we'll kind of get further with this in terms of what it means. For now, we're just practicing and being able to do it. Okay, you guys could do up to the third derivative even if you're asked. Okay, which would just be denoted as you would expect, 3 ticks, d cubed over dx cubed, okay, etc. So we could find the third derivative if we want to, and you're doing that in your practice. Okay? She's very mad. Hey, we don't know. 2 lessons, you know, the table might swing. We're not sure yet. Okay, any questions? So, okay. Okay, so this one, just for practice, it doesn't matter. We're going to find 5 derivatives of this. The first 5 derivatives. Not difficult. Okay, so what's the first one? What do you got for the first one, Rye? We'll go around the room. 4x to 3? Yeah, whole thing. Okay, good. What is the next one? Do you want to try the next one? Okay. Rachel, you want to try the next one? Or no, Abby, sorry.
24x plus 12.
Okay. Jeremy? Okay, well, it's just an x. So what's the derivative of just an x? Yeah. And what's the last one, Rachel? 0. The 5th derivative would be 0.
What? No. What does that look like if there's no rate of change?
Flat line.
The rate of change really.
Well, yeah, but the 5th derivative might be a little excessive. It's just the point that you guys can do it. Okay, in terms of getting there. And guys, trust me, we'll get there. We'll get there on applying this. You're not ready to know how to apply this yet, so I don't know why you're asking.
Easier to like wrap your head around.
I know. We got to build up to get there. Okay. Okay, last example coming. A little bit longer here, so this might, yeah, very. Okay. Very difficult. Okay, if x cubed plus y cubed equals 5, use, timeout. That's our last lesson, so we're going to pause for, yeah, we better pause. Okay, we'll stop there.